Good afternoon, everybody. Welcome to my talk on the high-performance data structures in Boost. I'm not really sure how I should start my talk. I guess you guys have all been to the keynotes from Liza in the morning, which was a lot about math and logic and references to some important people who invented or found out something 50 years ago. Compared to her talk, my talk is so boring and so easy to follow. So I hope you won't be disappointed that it is not as challenging as maybe Liza's talk was in the morning. So this is a talk on the Boost C++ libraries, and as far as I've seen, it is the only talk at this conference that is explicitly about the Boost C++ libraries. And I'm happy that I'm not standing here in front of an empty room. We had yesterday at 5 o'clock the Boost meeting, which was taking place in the launch. There are these social events that are happening while there are talks being given. And yesterday for the Boost meeting, there were 2 people. One of them was me. I think the group grew after half an hour by 50% because a third person showed up. So I was a little bit afraid already that today I will again be standing in a nearly empty room talking about Boost. We did talk about Boost yesterday for an hour, but it was a very, very, very small group. So this is a talk for 60 minutes where we can concentrate on Boost and on some Boost libraries. And the Boost libraries I'm going to present are Boost libraries that have some kind of high-performance data structures. And I'm going to start my talk with a reference to other talks, which is a bit unusual. Usually I talk about something for 60 minutes and then I end my talk by referring those who are interested in reading a little bit more about the topic that they can find some more material and works from others somewhere else on the internet. But this time I'm going to start my talk with some references to other talks and papers because my talk is somewhat of a follow-up talk, some kind of a part 2 talk. So there are a lot of videos and papers on the internet, and I put here 4 references together. If I quickly go over them, in the top left corner is a talk from Chandler he gave 4 years ago at CPPCon with the title Efficiency with Algorithms, Performance with Data Structures. In the top right corner is a talk from someone who talked about designing for efficient cache usage only recently at Pacific++, the conference that takes place, I think, for 2 years somewhere in Australia or New Zealand. That is a talk, by the way, which I haven't watched myself yet. It was only uploaded a few days ago to YouTube. But somebody told me who watched this talk that this must be a really good talk to watch if you're interested in anything that is about efficient cache usage. Here in the bottom left corner, there's a paper called What Every Programmer Should Know About Memory, a rather old paper, nearly 11 years old now, from Ulrich Drepper, a rather famous paper. So for those of you who don't like watching videos on YouTube, they might want to read a PDF file. And what I've seen is that in 3 hours from now on, there will be actually a talk here at this conference in Track A from Jonathan Muller about writing cache-friendly C++. Now you might wonder why I'm referring you to all these different works. So I'm going to talk about high-performance data structures in Boost. And your first question will obviously be, what is a high-performance data structure? And in order to explain what a high-performance data structure is, I will need to talk a little bit about how computers work today. I will have to talk a little bit about the CPU, about main memory, about something in between, what we call a cache. I will have to talk a little bit about how the cache works. And you will have follow-up questions like, okay, if the cache is so amazing, why don't we use the cache instead of main memory? Why don't we put everything into the cache, for example? Then I will have to explain why this isn't possible or why it would be possible but very expensive. And if we go down this road, I would be talking for an hour about a lot of other things, but not about the high-performance data structures in Boost this talk should be about. So I will probably let you hanging, and you will probably hear some unsatisfying answers from me if you are really interested in the details of what makes data structures high-performance data structures. And if you want to find out yourself how all these details actually work, you find a lot of stuff on the internet, and maybe you want to go to that talk from Jonathan Miller in 2 or 3 hours. That being said, it is not necessary for you to read and watch all of this just to be able to follow my talk. So we are going to talk about libraries here, and some other smart people thought very hard about how do I create high-performance data structures, and then they put them into a library, and because they put them into a library, we can benefit from their work without us having to understand all these details ourselves. Right? The usual reason why we use libraries, somebody else did the work, and we can just reuse their work and benefit from that work. Sometimes you feel like you need to dive into these details later just because we are programmers, right? We need to know everything. And if you have seen a few high-performance data structures, you want to understand better why are these data structures high-performing, what can I do to build my own high-performing data structures from scratch. So you go down this road and you try to read as much as possible. And once you go down this road, there's no end, right? There's always more you can read and always more you can watch. And I'm also talking about this because as we are all here at a conference, and I guess a lot of us are very good in C++, there are so many talks, so many other people who know so much more about you that it makes you feel small and unimportant, right? You go to this conference and you're supposed to learn a lot here and to go back to work on Monday really enthusiastic because of all that knowledge and all that enthusiasm you have seen here at the conference, but at the same time you feel like everybody around me knows so much more than I do. I must be the stupidest person in the room. So if we talk about these high-performance data structures in Boost today, it's perfectly fine if you stop afterwards, if you don't dive into all these details. It depends really what your goal is. If your goal is to be the best developer in the world building high-performance data structures, you probably want to watch and read everything you can. If your goal is to be the best developer creating commercially successful products, you probably want to find out how can you apply all that knowledge from experts in the most efficient and most effective way in your products. So you don't need to know all of that, what the experts know. You need to figure out how can I make use of that so that the customers and users of my products will have a better experience. And this is what this talk is about. So as you guys see, I'm trying to manage expectations. This is what this talk is about, and this is what I would argue are also the Boost libraries about. So I'm going to stop my presentation. I don't have that many slides. I have much more code. And I will open a first example, a very simple one. And we will look at a couple of variations of that example through the next 50 minutes. So if you watch the talk from Chandler, or if you read the description of the talk Jonathan Miller will give in 3 hours in track A, then the executive summary of those talk and probably that other talk from Jonathan Miller later is that you should not use any other data structure than a vector. Always use a vector. So we know that we have all these different containers in the standard library. Right? There's also a list, there's a set, there's a map. We probably all studied the interfaces, and we know a lot of reasons why we want to use the one container in one use case and the other container in the other use case. But if you watch Chandler's talk, at the very end he will say, no matter what you're going to do, no matter where you are going to store your elements, always use a vector. As I said, I'm not going to explain now in detail why he said this. There are all these other talks and papers you can watch, but this is where we start now. So I have now a very, very simple program, which does something very stupid, but I will walk you through. And this program uses a list. And then afterward, we look at the very same program, and the only difference will be that I don't use a list, but a vector. Then I'm measuring the time it takes to execute that program. And if Chandler is right, and all the other experts that talk about the cache on the internet, we should see that the program that uses the vector is faster. So what does this very simple program do? I create here a range of integers from 0 to 10,000. Details don't really matter, but 0 is inclusive, 10,000 is exclusive. So I have here 10,000 integers from 0, 1, 2, 3, and so on, up to 9,999. And then I'm stuffing all those integers into my list. And then I have here a sum variable. And at the very end of my program, I write the sum to standard out. And here in this scope, I calculate the sum. I'm doing this in the most stupid way possible. I'm iterating over my range that I created up here. And I'm looking for the number in my list just by using that standard algorithm. And once I found the number in the list, I add it to sum. Really stupid. Nobody would add up numbers like that. But I need to come up with some kind of algorithm so that I can actually measure the time. But if I was just adding the number directly, there's a very famous formula from Gauss. Hey, I actually have a reference to some mathematician. Then it's possible to add numbers much, much faster and much more efficiently than iterating over the range and then iterating over the container. But I'm doing this more as a demonstration to explain that indeed vector in this use case is a better container than list. So I also use here another class from Boost, a Boost timer, auto CPU timer. It's a class I can use to measure the time, and the time is measured from constructing that object up to destroying that object. So something in the constructor of that class will start a timer, and the destructor will stop the timer, and the time measured is also written in the destructor to standard out right away. So there are other classes in Boost Timer where I can play a little bit around with those features, but this is an auto CPU timer which does one thing and one thing only, and that is exactly what I need here. So super simple, and I hope everybody can see what the program does. So if I run this program now here, obviously, it depends on the hardware you're running the program on. So if you run the program on your hardware, you might have different numbers. So the number I'm actually looking at is this one here. That's the first one. There's a little bit more output from that auto CPU timer, but the other output we can ignore. And this is just the sum of all the numbers, which are also output here for no specific reason. Actually, when I was working initially on these programs, I thought, well, I'm not really interested in the sum, right? I just want to add up those numbers, and I want to measure the time it takes for this algorithm to work. So I didn't output the number, and then when I measured the time, I got always the same times for all my programs, because the optimizer was smart enough to see, hey, you're not using sum, so just optimize all that code away. And I was like, hey, damn, I cannot demonstrate that the vector is faster than the list. So that's the reason why I output this sum now. So when I look now at how long it takes for my program to add up all those numbers, I can see that with a list, we are at around 155, 160 milliseconds on this machine. Rather old one, but doesn't really matter. We just want to see what these times look like relative to each other. Now take the very same program, and I can jump a little bit around. The only thing I changed is that I don't use the list anymore. I use the vector. If I run now this program, we can see that this program is much, much faster. Right? We had something like 160, 170 milliseconds before, and now we are at 32, 56, 33 milliseconds. And the only difference is that I use a vector now. Now, if you guys know something about how our computers work, about how the cache works, this won't be a surprise for you. But if you look at it from a very naive point of view, if I ask my mother what she would expect, she would look at the algorithm and say, you're doing exactly the same amount of work as you do in the other program. So why should this program be suddenly faster than the other one? And in fact, a lot of people of us here in the community like looking at Godbolt. I assume everybody knows here about this online compiler, and then they copy and paste code into Godbolt, and then they look at the number of instructions, and if the number of instructions they get is shorter, if there are less instructions generated by the compiler, everything is great. Right? We know it's now more efficient. There are fewer CPU cycles used to execute your program. So I copied the source code of my two sample programs here already into Godbolt because I wasn't sure whether I have internet here. So on the left side, we see the program that uses the list. On the right side, we see the program that uses the vector. And if I just look here at the number of instructions I get with, I think I'm using Clang here, with -02, then I get 99 instructions on the left side for the list, 182 instructions on the right side with vector. So again, if you didn't really spend more time thinking about what you're doing, you would look at it and say, hey, the left program must be faster. There are fewer instructions being generated. There are fewer CPU cycles used. But we all know that this is not the case. We have just run the program, and if you read more about how our computers work, if you read more about how the cache works, you also will understand that it's not just the number of instructions, it's actually the time it takes for the instructions to receive data from memory they want to operate on, and that's where this optimization comes in. Hardware engineers came up with this thing called cache, and so on and so on and so on. The more I'm going to talk about all of this, the less time I have for the data structures in Boost, so I have to stop eventually. But that is just for those who always look at the number of instructions and say, yeah, hey, shorter instructions, everything is great, everything is better. So we have now seen that indeed, in this specific use case, in this sample program, a vector is better than a list. And we know that there are other containers in the standard library, like a set. So again, the very same program, just like with a vector, now with a set. And if I run this program with a set, it won't be a surprise that this program is far slower again compared to the vector. So with the vector, we had something like 30, 35 milliseconds. Now here we are at 300 and whatever milliseconds. Now let's finally look at the first container the Boost libraries can provide us to help us out. There's a container in Boost that is called flatset. It's in a library called Boost Container. And the library is called Boost Container because it provides implementations of all the containers you are familiar with from the standard library. So in Boost Container, you actually also find a vector and a list and everything else that you know from the standard library. But you will also find additional containers like that flatset that does not exist in the standard library. And that flatset is called flatset, as internally that flatset simply stores data in a sorted vector. So the way how data is arranged in memory is just like we would expect if we stuff that data in a vector, but because it is a set, it has to be sorted. That if you use the familiar interface of a set, that you can look up data with the kind of time complexity you expect. This is complexity, log n, and so on. You guys know everything about this. So this flatset has the very same interface, the very same member functions you would expect from stdset. But if I run now this program, I'm down again to those 30, 35, 40 milliseconds, as we have seen from the vector, because internally the data is just stored in a vector. Obviously, we do not only have a flat set, we have also a flat map in that library. I don't have an example for this, but flat map works accordingly. Now, I mentioned a couple of times the cache, and I created one sample program, that's the next one I'm going to run now, to see what kind of data there is that will help me to understand what my cache looks like. And with my cache, I really mean the cache on my computer. So I'm using here the Windows API. Obviously, I'm running on Windows. And if I use the Windows API, I can see that I have 3 cache levels. So there's cache level 1, 2, and somewhere down here 3. And that I have, when I look at cache level 1, I somehow have 4 different caches at cache level 1. The reason is that I have 2 CPUs here in my computer. So each CPU has a cache level 1, and each CPU has 2 types of cache level 1, one cache for data and one cache for instructions. And then somewhere beyond that cache in cache level 1, there's a cache level 2. Again, I have 2 because I have a dual core computer here. And further away, I have a cache level 3, and there's only one cache, a cache that is shared by my both CPUs. So we can also see that the sizes of the cache, they grow the further we go away from our CPU. So the cache that is actually built into the CPU has a rather small size of 32 kilobyte, and the cache level 2 is a little bit bigger, 256 kilobyte, and then cache level 3, 4 megabyte. So every time the CPU needs to execute instructions that need to do something with data, that data needs to be loaded from memory. And if you use an Intel chip, it has to be put first into the cache so that the Intel chip can read the data from the cache. And if you have a computer that has a couple of gigabytes in main memory, you will see already that all of that doesn't really fit into the cache, right? The cache is rather small, so it's some kind of a bottleneck. And somehow the computer decides itself what data to put into the cache when. Right? It's not that I have written anything in my program that would manage the cache. The cache is somehow managed by the computer itself. That's a good thing, because if you imagine you are writing a program and you decide, hey, there is some data in my program I need to have access to very, very often, and you could write code to reserve some memory in the cache for your data, well, probably every other developer writing all the other programs on your computer would do the same thing, right? And I'm running here PowerPoint, I'm running a browser, I'm running an antivirus program. If all those companies that are working on all these different programs were trying to reserve data in the cache themselves, it would be a problem, right? It's good that this is managed transparently for all those programs running on this machine. So how does this now actually work? So when we look at the sample program where I continuously iterate over data in my data structures, somehow, as we have seen, the program is much faster when it uses a vector than when it uses a list or a set. And the reason why that works is that hardware engineers came up with this great idea of putting this cache between CPUs and memory into our computers, because they saw that the CPUs have been becoming much faster than memory. So our CPU can do much more work in the same amount of time than we can actually receive data from memory that the CPU needs to operate on. So if you have a lot of instructions in your code that need data from memory to somehow add up numbers, for example, the instructions could actually run much faster, but they can't run as fast as the CPU could execute them, because it takes some time for the data to arrive from memory in the CPU. And then the hardware engineers thought about it and said, hey, maybe we can put something much closer to the CPU, let's call it cache. And if we can somehow make sure that the data is in the cache before the instructions are going to run that will need data from memory, if we can come up with a strategy that this data is already in the cache, in the CPU, then we can speed up our programs. Speed up as in we don't need to stall the CPU as often anymore, because the instructions have immediately access to the data they need. And the way how this works is that when we have, for example, a loop, like in the sample program we were looking at, and we access the first element in a data structure which we iterate over about, then when we access the memory to read that int, I think in my sample programs I'm using int, then it's not only that this one int is copied from memory into the cache to make it available to the CPU. In fact, there's a little bit more memory beyond that int put into the cache. And this is what we refer to as cache lines. So there are these cache lines of 64 bytes, and every time you're accessing a little bit of memory in what we call main memory, it's not just that this little bit of memory is made available to the CPU, it's actually a block of 64 bytes that is copied into the cache. So when we access the first int in our iteration, when we loop over a vector, that first int is moved into the cache so that the CPU can access it, but it's not only the first int, it's also everything else beyond that first int that fits into that 64 bytes. And if you iterate over something, that's just perfect, because in the first loop you access the first int, in the second loop you will access the next int, and 2 ints easily fit into 64 bytes. And so the next int is already available when we try to operate on the second item in our data structure. So if you use a vector, and with a vector, data is aligned as a memory block in RAM, blocks of 64 bytes are copied into the cache, and when we iterate over data, that guarantees that the next data is already available in the cache and doesn't need to be fetched from some other location in memory, something that needs to be done if we work with a list or with a set. So these are as much details I want to give to explain a little bit what's going on here, and why a program which does exactly the same as another program, which has exactly the same algorithm, can be faster, can have a higher performance just by using a different data structure. Jonathan Müller in 3 hours is probably going to talk about this much more in detail. All right, now we learned we are supposed to use always a vector if we want to achieve a higher performance. So somebody could say, okay, I have in my program a lot of objects, but I have actually pointers to those objects. So I'm going to follow your advice. I just put all these pointers into my objects. I'm going to iterate over that vector. Everything will be good, everything will be great, right? Well, obviously not. It will be possible to iterate very quickly about those pointers, but as we have just seen, if 64 bytes are copied into the cache, then it's 64 bytes of pointers that are copied into our cache. But then we have to dereference the pointer, and who knows where we have to dereference the pointer to. So we have to access some memory somewhere else, which is not necessarily in our cache yet. And so if we run this program, obviously it won't be as fast. So what we can do, obvious solution is that we actually don't put, I'm not going to run every program, we can just put the objects into our vector, and if we now iterate over the vector, everything is great again. Now you might say, yeah, that is maybe great for here, but I work on software where everything is created with new on the heap, where I have pointer all over the place, and I have to manage those pointers in some data structures, so I cannot just move all my objects that are created with heap that easily into a vector. Now here the Boost libraries come again to the rescue. So here I have a simple example first where I try to come up with a very simple class hierarchy. So I have a base class called object, and I have a derived class called derived. Just for fun, I made these different classes. I made sure that these different classes have a different size so that we cannot easily put objects of these classes into a vector. So then I have a vector with a pointer to the base class, to object. Now I copy here the pointers to objects into my vector. That is either a pointer to an object or a pointer to a derived object. So in this case, every second object is the same. Then I'm iterating again over everything and just add up the numbers. So this is a kind of code you might have in your own software, that you have a class hierarchy and you have a pointer to a base type, and you cannot easily come up with something now where you say, okay, I still want all the objects and all the derived objects in one vector, right? How am I going to do this now? This is where the Boost libraries can help you again. There is something in Boost that is called a poly collection. The library is called Boost Poly Collection. And there's a class in that library called base collection, and that base collection can be used just in this use case. So you have a class hierarchy with a base type, here's something derived. Usually you work with pointers to the base type, but what you can do now here, you can create a base collection of type object, that is your base class, and then you can stuff your objects into that base collection, and it doesn't matter whether it is an object of the base type or of a derived type. Everything fits into this base collection, and then you can iterate over it again, and you get your result. So I'm going to run these two programs now, the vector with the pointers and now the base collection, so that we can see that the base collection is actually having a better performance. Oops, that was wrong. So the program is working slightly different. The algorithm is different. That's why it isn't measured here in milliseconds, but in microseconds. But doesn't really matter. So we have something like 500 microseconds. If I run now the other program with the base collection, we will see we are down to 290 microseconds. So the question is obviously what's going on here, how does this work? And what the base collection does is it has internally a couple of vectors. And once you put an object into that base collection, so an instance of class object, it will copy those objects into a vector for this type. And if you add an object of a derived type to the very same container, the base collection will internally have another vector where the objects of this types are copied into. So the base collection is a little bit like having two vectors, one vector with objects, the other vector with deriveds. And when you iterate over the base collection, you will actually iterate first over the vector with objects and then over the vector with derived. So base collection is a little bit different from a vector because when you stuff objects in a vector, you know that the objects are stored in the very same order as you add them to the vector. With a base collection, the order isn't guaranteed anymore. Right? You will always iterate first over objects of the same type before the iteration continues with objects of another type. This gives you a higher performance because you have, again, everything nicely together in one memory block, and you can, again, benefit from the cache. But it's a bit different now because if the order matters to you, you probably shouldn't use a base collection. Now here in this example, the order doesn't matter to me because I'm just adding numbers up. I just want to have a better performance. Base collection also works with abstract base classes. So here I have an abstract base class, again my object with a couple of virtual member functions. I have a derived and a derived2 class where I find the data, and I can create a base collection with that abstract base class, and I can then still add objects of the derived classes to it. So this is something which could be useful if you have programs that are based on the good old object-oriented pattern, right? Gigantic class hierarchies, everything is slow because of a lot of indirections. Then trying to use the base collection could be something that gives you a better performance. There's another class in Boost Poly collection that works a bit similar to the base collection. And I will first talk about the sample program that doesn't use the Boost library. Let's say you want to store callables, functions in a vector. Then this is what you would probably do. Right? You would access the class stud function from the standard library, and you would say, okay, I want to be able to store anything in this vector that can be called according to the signature. No parameter, return value of int. Now I have defined two classes here that both provide a function operator that has that signature, so I can create objects of these two classes and I can add them to that vector. And everything is good again. I can iterate over my vector, I can call those functions, and everything is great. Now, for that case, you can also use a container from Boost that will give you a better performance. Because if you know a little bit about how stud function works, then you know probably about type erasure, that there's also some kind of indirection in stud function. There's some kind of a hidden class hierarchy with a virtual function. And all of that leads to less performing code. So you can get around that by using a class from Boost Poly collection that is called function collection. So the other class we just have seen was called base collection for class hierarchies with some base classes. Function collection is the class you can use if you have containers that store std function objects. The function collection is actually rather simple. So all you do is you pass here the signature of the callables that you want to be able to store. So again, I say I want to be able to store anything here that is callable without a parameter and that returns an int. And then I add my objects here again of different types. So all of them, again, obviously have to support that function operator. And then again, I'm calling those functions here in my loop and add up all the numbers. So if I run these two programs again, just to see what the numbers actually look like. So that's the one, the vector of functions. So we are at around 170, 180 milliseconds. And if the other one, the one with the function collection from the Boost library, then we are at 150. Is this really the right? Okay, we are a little bit faster. Not that much faster, but we are faster. So this is the one where I've been using the function collection. You don't get that much of a performance improvement as we have just seen, but it's still better than nothing. Now there's a third class in the library Boost poly collection, which we can look at. So we just looked at base collection, now we looked at function collection. There's a third class, which is called any collection. That class is interesting because it is based on another Boost library called Boost type erasure. And I have to maybe talk a little bit more about std function now. So I think if you are familiar with the standard library, you have seen std function before. And I think you take it for granted that std function somehow magically allows you to store objects of different types as long as all those objects have an overloaded function operator with a specific signature. So these objects, they don't need to be based on types that are part of a class hierarchy. These can be objects of separate types, and this somehow works. And the concept that this allows us to build code like that is type erasure. And if you think about it, std function is really just an example of a class that uses type erasure. Std function requires that anything you store in a std function object has to have a specific interface. And std function defines that interface as the thing has to be callable like a function, and it has to have a specific function signature. But you could come up with other types that work just like std function that require other interfaces, so that something doesn't have to be callable, but that something must have a member function called get. And there is a library in Boost called Boost type erasure that allows you to define those user-defined types. So in a way, you could use Boost type erasure to define a type like std function, but you can use Boost type erasure to define a lot of other types too. And Boost any collection is based on Boost type erasure. So with Boost any collection, you can create a container that says you can store anything in this container as long as what you store has a specific interface. And when I say has a specific interface, I don't mean the kind of interface which we are known from class hierarchies in C++. I mean the kind of interface as we know from other programming languages like Python. So if it quacks like a duck, it is a duck. Right? These types don't need to be based on classes that are all linked together in a class hierarchy. So if I use Boost any collection, I have to specify what that interface has to look like, so that I can only add items to that container that have that interface. And in order to define that interface, I have to use that other Boost library called Boost type erasure, because Boost any collection depends on that other library. So here I have to specify somehow what that interface looks like. And I do this here, get interface. And I'm saying the get interface is an interface that must have a get member function. I get member function with this type, no parameter, a return value of int. And by the way, it has to be a const member function. So I guess when you see this for the first time, it looks a bit weird. There's also this macro that has to be used here. So this is all coming from Boost type erasure. And this allows you to define an interface without having to use a base class and deriving your own classes from that base class. So I have now here my two classes again, object and object2, and as it happens to be, both classes define a member function called get, and both member functions are const. Both member functions don't expect a parameter. Both member functions return an int. Awesome, right? This is exactly what we want to see when we talk about the get interface. Now we can actually add those objects to our container, to our any collection. And the any collection is fine, right? Because all of that, what we add here, has a get member function. And then we can iterate over our boost any collection, call the member function get on all those objects, right? It's guaranteed that all these objects have a get member function. And I can again add up all my numbers. So if you want to do something like this in C++ without that boost library or any boost library, your C++ code would look probably like this, right? We have a std_any class in C++, in C++17, and you cannot really specify that the objects you would add to a std_any, that those objects have to have a certain interface, right? You can really add anything to a std_any variable. So I can easily add an object here or an object2, but then when I access a std_any element in my vector later, I need to do a cast, right? I need to know somehow that I'm now working with an object or with an object2. So I need to write a little bit of more code here and figure out how do I need to cast my any to the actual object I want to work with so that I can call the get member function. But I think you get the idea. Instead of doing this, this is again faster. You could also argue this is not only faster, this is also just by reading the code better, because you can more easily understand what should actually be allowed in this container, while with the vector here you can indeed add just anything, which might be a problem further down when somebody starts to adding items, starts to accessing items in the vector. So again, if I just quickly run the code, just to see again what the numbers look like. So that was the any collection from boost poly collection, a little bit less than 150 milliseconds. And if I run the any vector, let's see what kind of numbers we get here, 240, 250 milliseconds. So boost poly collection has these three classes: base collection, function collection, any collection. I think the base collection is the one most people would use. Function collection is also rather useful. Any collection is a rather specific use case. But these are classes that have been created in that library specifically with high performance in mind. And it all comes down to storing the actual elements that are added to those containers as a vector internally, so that when you iterate over those items, that you benefit from the hardware, from the cache, and so on. Now, you could say, yeah, well, it's great, the advice that I should always use a vector, but maybe sometimes I have good reasons not to use a vector. Maybe I want to use a list. I guess you guys all can come up with reasons why you sometimes want to use a list. For example, because when you have an iterator into a list, the iterator remains stable no matter whether you add or remove other elements in that list. So let's say you don't want to switch to a vector. You want to keep on working with a list. Here we have a list with objects, nothing spectacular. Again, add a couple of objects to my list, iterate over the objects, add up some number, rather boring. Let's say I really want to work with a list. I don't want to change my list to a vector for whatever reasons. Then there's another library in Boost that you could use called Boost Intrusive. And Boost Intrusive is a little bit weird when you see it for the first time. So what I'm doing here now, I'm replacing std list with a boost intrusive list. And now I'm adding my objects to that intrusive list. And in order to do that, I actually need to change my objects. I cannot just add any object to an intrusive list. I cannot add, for example, strings to an intrusive list. What I have to do is I have to add so-called hooks to the class that I want to use in my list. So if I want to store objects in my list, I I need to add these hooks to my list, to my object. And I can do this, for example, by deriving my class from a so-called list base hook. Now, the reason why I have to do this is that the Boost intrusive list does not copy elements when you add them to the list. So when you call pushback or placeback or any of those member functions that we are used to with the containers from the standard library, you know the data is always copied, right, into the vector, into the list, and so on. If you use the Boost intrusive containers, data is not copied. So the object you pass to a function like pushback is added to the list as is. And that means that there has to be at least one pointer in that object somehow, so that this list item can refer somehow to the next item in that list, right? If you add items to a list, they have to be chained together. So there have to be pointers in those objects that you can have a list in the end. So these pointers have to become somewhere. There has to be some memory in the objects that the intrusive list can access that memory and somewhere store the address of the next item in the list. And this is where you have to use those hooks. So we don't really need to understand what is passed from that hook here to our class, but we can assume that there are probably two variables in that base class for a pointer to the next item in the list and for a pointer to the previous item in the list. So when you have an object with a base hook, with a list base hook, you can add it to the intrusive list as is. And that means there's no memory allocation anymore. The object isn't just put anywhere in memory, which again means that it is your responsibility to manage the memory accordingly. I'm cheating a little bit because I need to create now, of course, again, my 10,000 objects which I want to iterate over. So in order to add 10,000 objects to my list, I have to create these 10,000 objects first, right? I cannot just copy something because it's not a copy that will be added to the list. My list will want to see 10,000 objects. So I'm kind of cheating because I'm creating these 10,000 objects in a vector first. And then I'm adding those 10,000 objects in that vector to the list. The objects will be added as is to the list. And when I iterate then over the list, I actually iterate over the objects that are stored in my vector. So I have a list with all the benefit the list gives me. And at the same time, as I control memory management, I can make sure that the objects are actually stored next to each other in one memory block, like in a vector. Obviously, there can be now a lot of counter-arguments why this might not be a good idea, because once you start now adding and removing items, something you can obviously do now with a list, the memory layout changes a little bit unless you make sure that the vector kind of represents always the same sequence of items in the list. But you have here a couple of options, right? You have here another library in Boost that can maybe help you to work with lists more efficiently. So I assume I don't need to run this program either, because it's obvious if I run here over my list, it's actually iterating over the vector, so it is expected to be fast. So Boost Intrusive is interesting because it does not only have a list, it has also, for example, a set, an intrusive set. So it has, of course, all those containers you would expect from the standard library, but it goes a little bit further. There are a lot of very weird and specialized container, like a splay set, and though there are more options than you are familiar with from the standard library. So if for whatever reason you always thought, hey, there should be more implementations of a set in the standard library, like this weird thing called splay set, then you could also look at Boost Intrusive, because there's not only the set and a splay set, there are a couple of other set implementations that can also help to improve your performance. They always require you to jump through those hoops and use some hooks, right? It's not like that you could now, for example, use a splay set to store a string. Right? You can't just use the std string class. The std string class doesn't have the hooks that are required for the intrusive containers. So you always have to a little bit work around the requirement the boost intrusive containers impose on you. But otherwise, you find here a lot more specialized containers than you can find in the standard library. What you can also do, just a couple of variations, you can also use those intrusive containers if you have class hierarchies. So here I have an example with a simple class hierarchy with a base class, derived class, and now you can use boost intrusive list to link objects together that are actually based on different types, right? As long as all those objects have the hooks that are required by the boost intrusive list, everything is good. So this base type had the list hooks. The derived classes obviously also have the list hooks. So you can now create a couple of objects of this type derived, a couple of objects of this type derived too. And then you can link them all together in the same list. And if everything is again stored in two different vectors, you can again iterate very quickly over all these items. If you work with lists and for whatever reason you don't like to use the boost intrusive library, there's still another option. It's not really a data structure in Boost, but it is something I still want to mention because this is all about high performance. You could also use a allocator from Boost. There's a library in Boost called Boost Pool, and it has a rather simple allocator. It's not a very complicated library. I think there are basically only two classes you could use. And one is called Fast Pool Allocator, and the other one is called, well, Pool Allocator, not so fast. And I can use this allocator here together with my stud list, and the rest of the program is the program we have seen already a couple of times. And that program will have a higher performance because this allocator basically internally also allocates nodes in some kind of a vector. I don't want to talk too much about how this allocator works. As I said, it's another library. It's not really a high-performance data structure, but it is just yet another option to see whether you can improve the performance of your programs that way. We're nearly at the end of the talk, and nearly our time is over. I don't want to go too much into details anymore. I have a couple of more sample programs. We were talking now a lot about Boost Poly collection, about the Boost intrusive library. All of those containers are high performance because of the cache, as I explained, but there are some other libraries in Boost where you could argue that they also provide high performance data structures, even though their high performance maybe has nothing to do with the cache. So we have one library in Boost that is called Boost Log-Free, and that library provides log-free containers, data structures that you can access from multiple threads without you having to do any synchronization. So here in this example, I have a queue, and I have two threads down here. The one thread just adds items to the queue all the time. The other thread just reads items from the queue all the time. And if I use the queue from the standard, I obviously have to use some kind of a mutex. I have to use some locks, because the queue from the standard library isn't thread safe. Nothing special, but if we turn to Boost, there's a class called Boost, there's a library called Boost Log-Free, and we find a queue implementation in that library that we can use out of the box without having to do any synchronizations ourselves. And if you run then this program, which obviously doesn't use any logs, you will get, not surprising, a higher performance. Now the library is called Boost Log-Free, and you might already want to jump up. Hooray, all the containers from the standard library available in log-free in a way that I can access them from multiple threads. It's unfortunately not the case. There's really only a queue in Boost Log-Free, not a vector or a set or anything else. So if you want to use any other container in a multi-threaded program which isn't a queue, Boost Log-Free won't help you, unfortunately. And the last library I wanted to mention is called Boost Heap, and Boost Heap provides a lot of priority queues. I don't know whether anybody ever had to use stud priority queue in a program. I never had to use that class, but if you had to use that class and you wondered whether there are other classes similar to stud priority queue that can give you different time complexities with those member functions stud priority offers, then you find those other implementations in a library called Boost Heap. There are, for example, classes called binomial heap or Fibonacci heap, classes that just work like stud priority queue, but provide you different time complexities in regard of the member functions that these classes provide. We have 5 minutes left. I think it's now a good moment to wrap it up, and it's your chance to ask any questions if you have any. As I said, yesterday we were 2 or 3 people at the Boost meetup. There were not many questions, even so we managed to talk for 1 hour over Boost. So let's see whether there are any questions. Ivan.
Hi, thank you for the great talk. One question. You tested the function collection with kind of huge function objects. Did you benchmark vectors of stud function when functions are small enough for small function optimization?
Okay, that's a good question. You're talking about the small buffer optimization, small object optimization. No, I didn't do that, So actually, if you go to the documentation of Boost Poly Collection, you will see a lot of charts where the developers of that library try to prove themselves and for others that their library is actually faster or their containers are actually faster than others. But indeed, there can be many, many use cases where it doesn't make sense to use the specialized libraries or containers from Boost. So what I've been doing here also, I've been iterating over elements all the time, right? Mm-hmm. So if I use a set and I iterate over elements all the time, why do I need to use a set, right? Then I can also use another container like a vector. So obviously you use a set because you want to look up things quickly. And if you come up with other use cases, with other examples, you might not find enough reasons to actually give up the containers from the standard library and use something from Boost. So this is not a general advice. It's not like you can always use the Boost libraries and everything will always be better.
Okay, thanks.
Okay, thanks.
Thanks. My question is, what would you recommend to type erase the container itself? So I'm dealing a lot with shared library, and the kind of container I'm using internally is something I'd want to hide because I'd like to change it if I need it. Mm-hmm. Switching from list to vector depending on the amount of data and the operations I'm doing. So do you have any recommendation how to type erase the container itself?
Yeah, so when you talk about type erasing the container itself, I automatically think of Boost type erasure. Because I guess your containers are not necessarily part of a class hierarchy. So there's no base class that would define the interface every container has to implement. So or you wanted to say something?
It's usually an STL container.
Okay, indeed, yeah. So there is something all those containers have in common, right? That is something that you require. That is the interface that containers have to implement. But it is not encoded as a class hierarchy. It is not that the containers in the standard library are derived from a base class. And that's actually where you can indeed use Boost type erasure. So you can define with Boost type erasure an interface, just like I did here with the has to have a get member function. And if you define an interface like that, you can create a type and you can instantiate the type. And that type can then store any object, any container, as long as those objects provide that interface as you require. And in that way, you could indeed come up with something that hides the actual container. You don't know anymore whether you use a vector or a list or anything else, as long as all those containers implement the interface that you have defined with Boost type erasure. So I think Boost type erasure isn't really a library that is very much well known. And I actually mentioned Boost type erasure last year when I gave a talk here. And I'm not really sure whether it's a library that a lot of people use in production. But then again, if you want to do something like you just asked me, I'm not sure what other advice I should give. Okay.
Hello, thanks for the talk. What's your suggestion for string sets and fast lookup? And what about cache locality if you put strings in your collection?
Now, as you're asking me, there are other libraries I can think of in Boost that could be used. Session is over. All right. So maybe we talk about it afterwards, yeah? Okay. No, that's okay. That's fine. Yeah? Okay. I think there are even more questions, so maybe we do it here, yeah, afterwards. Then I guess, given that in 15 minutes the next session will start, people can slowly run out and have a coffee. Yeah? Okay. Thank you much.